Greetings, humanoids. Welcome to episode 8 in our class on philosophy of climate change. This is in module 2 in the third part of a series on climate science, as we looked at what is known in the kind of passive voice, climate science as a body of knowledge, and then we looked a little bit at climate science institutions, who's doing the knowing. And then today, briefly, we're going to look at climate science methods and tools. In other words, how is what we know known? How do we figure this stuff out? And what are the limitations of these methods and tools? And as with all of these lectures, this whole class really is very introductory. We're going to be just I hope to provide you with some categories for organizing a massive multidisciplinary, multi-method, multi-tool field that is climate science, right? So I studied a lot for this lecture, and I'm walking away with the sense that I know less than I did when I started, but maybe that's okay. So hopefully what I have to share is helpful. Of course, I'm here with Akbar. Did I show you? There he is. He has something to say about that at the end as well. He's going to help me navigate. Akbar, what do you want to do? Sit down? All right. There he goes. Okay, so let's jump into it. Gosh, here we go. New feature, Akbar reads the news. As I'm recording this is something that's in the news. California and Colorado fires may be part of a climate-driven transformation of wildfires around the globe. Talk about this in general a bit today. This is a statement of attribution, where you take some climate feature. In this case, we're looking at wildfires, and it could be in a particular place like Colorado, or it could be globally. And they mention even Australia and Siberia. And you're trying to make some sort of attribution to climate change. You're saying climate change caused this and somehow. And I think actually what we might want to start thinking is not so much cause as increased the likelihood of, or increased the risk of, and or increased the intensity of something, or the duration of something like a wildfire. This is the way climate change shows up. It's not a standalone issue. It's woven in with other things, and in a way it's kind of invisible, even though it's there as a sort of driving force underneath a lot of other things. In this case, you've got successful, end quote, fire policies over decades of suppressing fires, which has left a lot more material to burn. You also just have weather patterns that are always changing, right? You've got human development going on and human-caused fires. And then kind of underneath and woven through all that is climate change, right? So getting that disentangled is a lot of what climate science does. So that's in the news. As I speak, we also have 2 hurricanes ripping through the Gulf of Mexico. So here we go. What do I want to do today? And again, I'm going to kind of just be brief as I can be, knowing that this is an introduction to this whole field, and that what I really am trying to do is provide you categories and to guide your thinking. So most of my value added, I hope, is just giving you these kinds of buckets to organize stuff into, okay? So I have a few words to say about science in general, about its method, or really methods maybe, and tools, quantification in particular. And then we're going to get to climate science, and I'm leaning on a couple of sources I'll show you to put all of these disparate approaches into 2 main buckets. And then I've got subcategories within each of these to look at. And then we'll wrap up by just briefly a slide or 2 on the uses of climate science methods and tools. We talked about attribution already with the wildfires, detection and projections, which is something we'll have a recurring theme about when we get into science, climate science politics, and the use of science in decision making. Okay, so starting generally with science, I've got Halley's Comet here, and the top image is it's kind of a old catalog or calendar of bad omens. You know, so if you see the moon in a particular phase, or if the sun is doing this thing, or if you see a comet in the sky, this is what it means, right? Your village is going to burn, or something like this. This is a kind of mythical or narrative way of understanding the natural world, is that you have some sort of agents, some gods or demons or creatures that are in charge of sending these omens to you, and you have to learn how to read them. You know, a comet might be, oh, the skull of a god and pieces of it are falling down or something like that. But you're appealing to some supernatural agents, right? What makes science different, of course, is that it's a non-narrative form of rationality that appeals strictly to nature itself, that is, to the natural entities themselves and the laws that govern them and the logical relationships between these things. Now, why that matters is because if you're not just telling a story, just making something up, you have to have standards for testing or verifying or falsifying the claims that you make. That's what makes science really unique, is its appeal just to the natural world, and then its long-standing development of standards for figuring out what's a good method for going out and finding truth, and in a way that would correspond with reality. So Halley's Comet is in fact a ball of ice and rock, and we can find ways of empirically verifying that, or experiments that we could do that could try to falsify that, right? That's what science is all about. And another way to say is, or another strength of it is, you could call it the proof in the pudding, that it can make predictions. You know, Halley's Comet's a great example of, oh, once we understand this as a natural phenomenon, the laws governing it, we can then predict, in this case, very precisely when it's going to reappear, you know. And then, of course, science also, insofar as it can develop technologies that work, like airplanes, you know, that lends credence to the scientific method or methods. The method, capital M, I think, is this appeal to nature and the logical relationships between things, which has many methods underneath it. The implication, of course, and I've said this before, is that science is in a way epistemically special. Look, it's not the only way to understand reality and to come about truth. You know, a great work of art, for example, flashes insights and truths at you. A novel can ring true to your soul. So I'm not discounting other forms of truth, but science has this sort of epistemically special status. And as a result, it has this privileged access and power and decision-making. You know, not everybody's equal, right? What is it? Your Google search is not equivalent to my astrophysics degree or something like that, right? Okay, so that's, again, a reminder on why we're spending so much time on science. A bit on tools. That's a quote from Protagoras. I was thinking, when I jump in a pool with my kids, they think it's perfectly fine, but I think it's freezing, you know? Or if you come out of a sauna into the ice cold winter weather, it feels nice to you. Whereas if you would have just walked into it without getting all heated up first, right? So there's this notion that man is the measure of all things, that everything is relative to our sensorium. Well, scientific tools, in many ways, at least the way I want to talk about them, are attempts to abstract away from, and in some sense get an objective measurement or quantification of the phenomena that you're experiencing, right? So temperature as a scientific measurement is abstracted from the feeling of what is the room like now, right? So that it can be quantified, standardized, and then compared across time and space, right? Maybe this is obvious and basic, but I think it's worth recalling that to your mind, that that's actually really pretty far out. I put the sundial here too in the evolution of clocks, you know, time being quantified. There's a sense of time. It's lunchtime because I'm hungry. And then there's lunchtime because the clock says it's noon, right? So the development of tools in science to quantify, measure, compare, is absolutely essential to climate, right? And in the case of temperature, of course, this has to do with energy and its formulation in the modern scientific paradigm as this universal currency that can then be measured in these standard units that can convert across different forms of electricity, heat, or different forms of energy, like electricity, heat, and, you know, you name it, different forms of energy. Okay, so that's preamble. Let's give the climate. Think about the climate system. Enormously complex, full of kind of, what do I want to say, open-ended changing parameters all the time, long and deep periods of history. How would you ever go about studying this, something so big, so complex? Well, I think in a nutshell, the answer is you'd have to have lots of different ways to get at it, right? So climate science is a catch-all for a whole bunch of different ways. So I've tried to put those different ways of using methods and tools into two buckets, and I'm leaning heavily on these two articles, which I put in the notes from this class. And my two buckets are climate data and climate modeling. And within the bucket of climate data, I've got three sub-buckets. The first one is just station-based data sets. And here you got something on sea and something on land and then a satellite up in the sky. So you've got a whole bunch of data being gathered by different kinds of instrumentation around the planet. Now, if you think about what are the strengths of this is that it's actual observations, right? The weaknesses are, well, these instruments might not be calibrated the same way. We may not have them all over the planet where we'd like to have them. They might break down. We may not have had an instrument there for a very long time. It might be somebody built a building next to an instrument which changed the local heat or the temperature around it in a way that might invalidate its results. I mean, so there's all these weaknesses, but all of this built together is one of the important bases of climate science. This is something I just learned about. Reanalyses, retrospective analyses. If you think about it, even though we've got thousands and thousands of instruments out there, we haven't always had those, and we don't have them everywhere, and we don't have them in the whole column of the atmosphere or all over the ocean. So you have all of these time and space boxes with the gaps in them. And then you have those little pots, little spots here and there where we actually have observations. So one of the data sets there's a lot of these, are reanalysis data sets that climate scientists build and then use. Starts with observations, whatever you got, which is going to be limited. And then you use, and this is why models and my two buckets, models and climate data, are really intertwined. But you use basic simulation models of the climate system or weather systems to kind of fill in the gaps. And then as you get more observations, you tweak the models to fit better with what's actually been recorded. And then you have these reanalysis data sets, which climate scientists like to use because it kind of gives you a uniform grid-like pattern of data on climatological variables for them to work with. Third and last one I'll mention here, and I remember at grad school I studied from one of a paleoclimatologist at CU Boulder, and he used to go to Antarctica drilling ice cores and then reconstructing through these proxies what ancient climates looked like so that we can try to get a sense of long scale, way before we had machines, before humans were around to measure anything, what was the climate doing? Ice cores are one of these, tree rings, fossils, lake sediments, and a whole bunch more. Okay, then there's climate modeling. And I have a feeling we'll talk more and more about this as we go on. So let's just call this a first brush. But what is a model? I put a little text over here on the side from one of the articles I mentioned. A model, it's really an attempt to build a representation of the complex climate system. And of course, we don't have complete access to reality. And so any model is going to be a simplification of the actual system. But the idea is if you could build in enough of the laws that are governing the way the climate system works into a model, that you could then have this little representative world that you could run different scenarios on and try to figure out what's going to happen in the future and what's going on now. So a lot to say about climate models. On the right-hand side, this is just to say, look, climate models have gotten better as computing power has gotten better. So in the 70s, they could kind of account for emissions and rain, right? And maybe solar inflow of energy, right? And then in the 80s, they started adding other things. And then eventually you get the ocean, but the ocean doesn't have circulation because we didn't have the computing power to model that. Then you add ocean circulation, and then you can add sulfates in the atmosphere, which actually can often have a cooling effect, right? And we've added clouds along the way, although clouds are still really hard to understand and model when it comes to climate. And then you can see you go on and you add more atmospheric chemistry and you start adding vegetation, and you're trying to build in your models the real complexities of the Earth. On the left, you've got just an image of what these models, how they build these grids. And the bigger the square, the less resolution it has. And as the computers have gotten more and more powerful, you can make those grids smaller and smaller, so they have greater resolution in these models. Oh, I clicked on this Akbar. Here we go. This is just a quick thing. It's a little image from that article. It just shows you, again, modeling starting, gosh, when computers almost got strong enough for this in the late 50s. And they started modeling just maybe one feature or facet of the climate system. Like, let's just look at the oceans, or let's look at atmospheric chemistry. And then over time, all of these models have kind of merged and morphed as you got better computers into more holistic systems modeling going on. Lots of different types of models, and the categories are fuzzy, but I wanted to give you what I think is a pretty good categorization. So there's these GCMs, which can either stand for global circulation or global climate models. And then ESMs, which are really, they're Earth system models. They're really still GCMs, but they are juiced up to include more features, especially vegetation and biogeochemical cycles. So you can look at more of the real dynamics that are driving the climate system, and then therefore hopefully have a more accurate climate model. And then these IAMs, these integrated assessment models, take yet more into account by now building in the absolute wild card, humans, right? So, and in particular, what are we going to do with our greenhouse gas emissions? So with these IAMs, you can run different scenarios under different climate policies with greenhouse gas emissions to try to figure out how that would affect future climate. And you can even say, from there, look at how different scenarios would impact, let's say, ocean health or coral reef health. And then you could, from that, deduce or infer the costs of that, so you could kind of derive a social cost of carbon calculation from these models to say, if we don't cut carbon by this much, we're going to have these kinds of costs heaping up on future generations, right? So this, some of the things these IAMs could be used for. There's also regional climate models, which would only look at a particular part. For example, I'm interested in forest fires in western Colorado, and you've got regional climate models there that actually show that's a part of the world that's warming faster than average. Okay, so that's building the model. What's actually in the architecture of the model? Well, you've got what you know from the laws governing the behavior of the various climate systems. So what you know about what drives the jet stream, and what you know what drives ocean circulation and radiative forcing in the atmosphere, all of these things are governed by laws that we have been able to figure out more or less, right? You build that into the architecture, and then you've got your world ready to run, this representative world. What do you put in it? Well, the inputs would be these forcings, and in particular, what we're interested in, insofar as we're looking at climate change science, are emissions, greenhouse gas emissions, right? So you run the models on different emission scenarios, and we'll talk about this more. The most important version of this are these RCPs, representative concentration pathways, which the IPCC uses. These are plausible descriptions of the future based on socioeconomic scenarios. In particular, they ask things like, well, if we peaked greenhouse gas emissions in 2030, what would the future look like? If we didn't peak until 2050, what would it look like? If the peak was this high, if it was only this high, what would it look like in the future? And then what do you get? That's what you get chugging out of it, is a picture of what the climate system looks like under different kinds and amounts, with different kinds and amounts of variables. So you can say, well, this is what temp will be doing, precipitation. You can even look at maybe the likelihood of extreme weather events. That's what decision makers often want, is to know, if we do this policy, what will we get for it? And they lean on these models to try to help them figure that out. You also get a sense of climate sensitivity from these models. That is, how sensitive is the Earth to increases in greenhouse gas concentrations? And this has been something they're making a lot of headway on now. And it's a really important thing, because if, for example, temperature and extreme weather events don't really budge that much with increasing greenhouse gas concentrations, well, then it's less urgent to act. But if these variables are really sensitive to greenhouse gas concentrations, then it's more urgent that we act. Okay, and then I'm not going to click over here. I put this link in for you. There's really interesting things where you can try to confirm climate models. That is to ask, let's compare the model with actual observations. So especially once you've got historical data accumulated, you can say, well, here's what the model said was going to happen. Here's what actually happened, and you compare them. And it turns out there's a lot of models out there. Many of them actually have done quite well. Okay, wrapping it up now. I know it's a little bit longer than the usual lecture. 3 uses of climate models. So detection. Did the climate change? I put the IPCC quote here. So can we see a difference in the climate system that we know is not just a matter of internal variability? In other words, of course, there's all sorts of change. Weather's changing all the time. But we actually seen a climate change, right? So we're trying to detect that. Now, without providing a reason for that change. But that's the second thing, attribution. So what caused the observed change? But like I said with the wildfires, maybe not so much cause as increase the likelihood or increase the severity of it. By the way, there's also even extreme event attribution. So you can have, see where I said put the consensus position there, that it's virtually certain that mean surface temperatures have increased since 1950. So that's detection. This is IPCC language. And it's extremely likely that more than half of this increase is due to anthropogenic GHG emissions. That's attribution. So detection, yes, the climate is changing. In particular, we know it's warming. Surface temperatures are warming. That's detection. Attribution, well, at least half of this is caused by anthropogenic greenhouse gas emissions. That's what's known as the consensus position. There's some debate on that, of course. But attribution can even go smaller, and that's where the cutting edge of the field is now, is can we look at a particular event like a wildfire in California, and can we tie climate change to that event with some specificity? And if we could, even from there, think about it, could we then tie responsibility for that event to particular polluters, those who have put the most carbon into the atmosphere? Okay, that's kind of in the legal frameworks that are just emerging now. I don't know where that will go. And then, of course, projections, that the uses of these climate models, people want to know, if we do this, what's going to happen? That's so much of climate science politics. Okay, summary real quick. Climate science, multi-methods, multi-tools, multidisciplinary. What is using theories and natural laws about what we know about how the climate system works. These explain how it works. Our observations, like the measurements we're getting from satellites and land and sea-based observation sites. And then models, which can take observations and these natural laws and try to build these simulation worlds to help us understand, explain, and predict the climate. So that's kind of what we've been talking about. There's a lot of research out there, and it's growing and growing. And there is, I think, this broad consensus position that I just mentioned, but also, of course, tons of ongoing debates and uncertainties in the literature. What's going to happen with Greenland ice, for example? It's melting now at an increased rate. Will that continue? Could it reach a tipping point where it goes even faster and faster, or not? on that level, there's all sorts of research going on now and debates being had. And it makes me wonder, at least, I don't know if we should wonder, do we need more and more science, you know? What is it doing? Is that an end in itself, or is it a means to action? And if it's a means to action, are we doing good at translating science into wise action? And if we're not, well, what kind of research do we need for that? So those are questions to be thinking about in the future, but I know we got to sign out. Like I said at the beginning, and Akbar confirms, look, if you feel like you know less now than you did before I started yakking at you, that could be a sign of success. I think our eyes are open to just how much is going on in the climate science world. Hopefully I've given you some categories that help you to make sense of it all. Okay, well, until next time, may the force be with you.